Hello everyone, welcome back to this online class. My name is Francis Okech and my YouTube channel is Professor Francis Okech. Today we are going to look at Calculus 1 and our main topic is on the basic differentiation rules. In particular, we are going to look at the power rule, the derivative of a constant term, and derivative of a linear combination of functions. Now, these rules are derived from the first principle. They are simply formulas that you are going to be using. Instead of having to do everything from the first principle, there are formulas to aid us in finding dy over dx or f prime of x. To start with, let us look at the first rule, that is power rule, and this is how it states that if y is equals to x raised to n, where n is a real number, then dy dx is equals to n times x raised to n minus 1. I told you dy dx is the same as f prime of x, so they're the same. So we are saying here where n here is a real number. N is a real number. So n belongs to the set of all real numbers. Remember, real numbers are from negative infinity to positive infinity. So this is what you are calling the power rule of differentiation. What does it mean? That you bring down the power, then the resulting power is less by 1. I can explain this. It means bring down the power, bring down, that should be down, bring down the power then the resulting power should be less by 1. The resulting power should be less by 1. So when you bring down the power, you get n. Then now the new power of x is n minus 1. That is power rule of differentiation. And these rules, these are formula, yes. Somebody might be wondering, where do we get this formula from? This formula is derived from the first principle of differentiation. So we can derive it. I can write here derivation. Want to derive that formula or prove the formula. So what you're going to do is to say let f of x be equal to x raised to n. This means that our f of x plus h will be equal to x plus h raised to n. And if I expand this, use binomial expansion, this is the same as n combination 0, x raised to n, h raised to 0, plus n combination 1, x raised to n minus 1, times h raised to 1, plus n combination 2, x raised to n minus 2, h squared, plus so many other terms, plus the last one will be n combination n, x raised to 0, h raised to n. That's what we'll have. And remember, I want us to take note of combination. How do we define combination? Take note that n combination r is defined as n factorial over n minus r factorial times r factorial. This is r. So that is what we mean by n combination r. So when r is 0, we'll talk of n factorial over, remember when r is 0, so we now talk of n combination 0. That will now give us n factorial over n minus 0 factorial times 0 factorial. And 0 factorial is always equals to 1. Also 1 factorial is 1. So the answer here should give us 1, because the n factorial will cancel with this n factorial, and you know 0 factorial is 1. So instead of n combination 0, we are going to write 1 times x raised to n times h raised to 0. So the first term is simply x raised to n. Then plus, let's see, what about n combination 1? N combination 1 is the same as n factorial over n minus 1 factorial times 1 factorial. And this you can write as n times n minus 1 factorial over n minus 1 factorial times 1 factorial. And you see, n minus 1 factorial will cancel with this. So we have n over 1 factorial, which is n. So the answer here is n times x raised to n minus 1 times h. Then plus, let's see, what is n combination 2? So n combination 2, this one will give us n factorial over n minus 2 factorial times 2 factorial. And this is equals to n minus 1 times n minus 2. And this is factorial. Remember here we got n. Then over n minus 2 factorial times 2 factorial. And if I simplify, n minus 2 factorial will cancel with this one. So it's like we have n times n minus 1 over 2 factorial. N times n minus 1 over 2 factorial. And that should multiply x raised to n minus 2 times h squared plus so many other terms. The last one is n combination n. Let's also work it out. N combination n. What are we supposed to get? This should give us n factorial over n minus n factorial times another n factorial. So this will cancel. Remember what we got here was n minus 1 over 2 factorial. What about here? We are getting 1 over n minus n is 0. So 1 over 0 factorial is simply 1, because 0 factorial is 1. So you take note of that. So this is 1, and x raised to 0 is also 1. So what we have here is plus h raised to n. Very important. So that is our f of x plus h. So the next thing here is to now get the difference of f of x and f of x plus h. So we can now say that therefore, we can say therefore f of x plus h minus f of x, what will it be equal to? This is equal to, you can write it here, x raised to n plus n x raised to n minus 1 times h plus n minus 1 over 2 factorial x raised to n minus 2 h squared plus so many other terms up to the last one h raised to n. then minus x raised to n. And if you simplify, you see x raised to n will cancel with this other one, so that we have n times x raised to n minus 1 times h plus n minus 1 over 2 factorial x raised to n minus 2 h squared plus so many other terms plus the last one h raised to n. And so here, anything that is common can be factored out. Let me factor out what we call x raised to n minus, I can see h is common. So h can be factored out, h outside, so that what we have is n x raised to n minus 1 plus n minus 1 over 2 factorial x raised to n minus 2 times a 1h plus so many other terms plus the last one h raised to n minus 1. I have factored out h. So now let's go back to our first principle of differentiation. So using the first principle, using the first principle of differentiation, we have, so what will it give us? We need f prime. F prime of x is simply limit as h approaches 0 of f of x plus h minus f of x, and the whole of this is divided by h. And now we know the numerator and denominator is h, so when we substitute numerator, so that will be limit as h approaches 0. In the numerator, we found h times n x raised to n minus 1 plus n minus 1 over 2 factorial x raised to n minus 2 times h plus so many other powers of h, higher powers up to h raised to n minus 1. That's what we have in the numerator. Denominator, we have h. So we are dividing by h. And look at this. H will cancel with this. So it's like we have this limit as h approaches 0 of, now what we have is n x raised to n minus 1 plus, that should be a plus n minus 1 over 2 factorial x raised to n minus 2 times h plus so many other higher powers of x, or not x but h, higher powers of h, plus the last one is h raised to n minus 1. So once you simplify your function, the last thing is to try direct substitution. So when we use direct substitution, we are going to get, remember where there is h, you put 0, so we are going to get n x raised to n minus 1 plus, this one will be 0 because you see here, we are replacing h by 0. And what we have here is higher powers of h. So everything will be 0 because h is equals to 0. And 0 raised to anything is 0. So therefore, our answer here is n x raised to n minus 1. So we have shown that if you start with f of x to be x raised to n, then f prime of x should be equal to n times x raised to n minus 1, where n is a real number, either negative or positive or 0. So that is what you're calling the power rule of differentiation. And I want to give you an example. So this completes the proof. This completes the proof. Now let's look at just an illustration example. Find dy dx, dy over dx, given that part A, y is equals to x raised to 3, part B, y is equals to the square root of x, part C, y is equals to 1 over x. So let's work out those ones. Solution. In part A, dy dx will be equal to, you bring down the power which is 3, then x raised to 3 minus 1. And so this should give us 3x squared. That's the answer. In part B, remember something you need to take note of. Y is equals to root x. Root x is the same as x raised to 1 over 2. So therefore, dy dx is now bring down the power, that is 1 over 2 times x raised to 1 over 2 minus 1. And so this you can write as 1 over 2 times x raised to negative 1 over 2. And so this can as well be written as 1 over 2x raised to 2x raised to 1 over 2. When you take the negative power to the denominator, it becomes positive. And so this can be written as 1 over 2 root x. That's our derivative. Part C. Remember, y is equals to 1 over x can be written as x raised to negative 1. So therefore, dy dx is equals to, bring down the power, that is negative 1, times x raised to negative 1, you subtract 1, that will give us negative 2. So that is negative 1 times x raised to negative 2, which you can as well write as negative 1 times 1 over x squared, which is simply equal to negative 1 over x squared. That's our dy dx. So you see, power rule is very simple as opposed to the first principle of differentiation. First principle will take a lot of time, but power rule, just applying the formula, you get straight away to the required answer, the derivative. So this is all about power rule. I told you the power can be a real number, any real number. It can be positive, it can be negative, or it can be 0. So maybe I can give you another one where the power is 0. And you see, when the power is 0, then it is a constant. So let's say part D. Part D, we are told that y is equals to x raised to 0. X raised to 0 is 1. So what is dy dx? This means that dy dx will be equal to, bring down the 0, then times x raised to 0 minus 1, and 0 times anything is 0. So x raised to 0 is 1. Take note of that. And you see 1 is a constant. So it means when you differentiate a constant, the result should be equal to 0. Because x raised to 0 is 1, which is a constant. And when we are differentiating it, we are getting 0. So that's a point you need to take note of. Note. So derivative of a constant, or let it not be a note, let it be number 2. The second rule is derivative of a constant term. When you have a constant term, how do you differentiate it? So this is what the derivative looks like when you differentiate a constant term. We are going to state it. You write this. The statement is this one, that if y is equals to a constant c, if y is equals to a constant c, then dy dx will be equal to 0. That every time you differentiate a constant, the result should be equal to 0. Let us derive this one. Derivation how do we show that when you differentiate a constant, we get 0? So you say let f of x be equal to a constant c. So this means that f of x plus h is still the same constant c. So therefore, f of x plus h minus f of x is the same as c minus c, which is 0. Hence, from the first principle, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x, everything over h. Look at our f of x plus h minus f of x. That is equals to limit as h approaches 0. We got 0 over h. And so this will be limit of 0, which is 0. Limit of a constant is the same constant. So the answer there is 0. That means our derivative is 0. When you differentiate a constant term, you need to get 0. For instance, let me give you two examples. Examples. We are told to find dy dx given that in part A, y is equals to 17. In part B, y is equals to negative 24. So in all of them, the result is 0. Let me choose another color. Can use red, or let me use blue. So here, this is a constant. So when you differentiate that, you get dy dx is equals to 0 because 17 is a constant. The same here. Negative 24 is a constant. So when you differentiate that, you get dy dx is equals to 0. Both of them are constants. So that's what you need to take note of, that when you have a term that is simply a constant, does not depend on x, and you're differentiating, then your result should always be equal to 0. Another rule is the derivative of linear combination. So you can write here, derivative of linear combination of functions. So what it states is this one. When you talk about linear combination, it's like you're adding or subtracting some functions multiplied by some scalars. That is what you're calling a linear combination. And this is what it states, that if f of x and g of x, if f of x and g of x are differentiable functions of x, are differentiable functions of x, comma, and a is a and b. A and b are constants, then derivative, let's say this, derivative with respect to x of a times f of x plus b times g of x, this should be equal to a times f prime of x plus b times g prime of x, where the primes denote derivative with respect to x. That is called a linear combination of the two functions f and g. A and b are scalars, they are constants. Now, how do we show this? Proof or derivation. You can derive it. So we are going to start by saying let y, of course y is a function of x, let y of x to be equal to a times f of x plus b times g of x. That's for y. I want to use first principle. So this means that I need to get y of x plus h. Therefore, y of x plus h is the same as a is a constant, f of x plus h plus another constant b times g of x plus h. Now, what about the difference of those two? So now we need to know what is y of x plus h minus y of x. That will be equal to, here we had a times f of x plus h plus b times g of x plus h. We are subtracting a times f of x plus b times g of x. And so this is equal to, let me open the bracket. You see, a is common. I can factor out a so that this can be written as a outside f of x plus h minus f of x. Then I can also see this another term with b, so factor out b so that we have g of x plus h minus g of x. Now that is the numerator, which is y of x plus h minus y of x. Now, using now the first principle, let me use another color. Using the first principle. First principle we have. So now you see, when we write dy over dx the same as y prime of x, which is also equal to f prime of x. Those are just the same notations, different notations for the same thing. So now I'll write now y prime of x, which you know is the same as dy over dx, which you also know is the same as f prime of x. So this will be defined as the limit as h approaches 0 of, now instead of f we are talking of y, so it is y of x plus h minus y of x, and everything here you divide by h. That is the first principle of differentiation. And we know the numerator, so this we can as well write as limit as h approaches 0. Our numerator we got a at f of x plus h minus f of x, that one. Then we also got here plus b times g of x plus h minus g of x. And the whole of this is divided by h. So, you know the properties of evaluating limits, that limits you can distribute it to each of those functions. I want to split this into two parts because it applies the property of limits. Now, this thing can be written as another color, can use red. It is still equal to limit as h approaches 0 of a into f of x plus h minus f of x. This you divide by h. Then we are adding this to another limit as h approaches 0 of b times g of x plus h minus g of x. This is over h. And you see a and b are constants, so they can be factored out so that this limit can be written as a times the limit as h approaches 0 of f of x plus h minus f of x. The whole of this you divide by h. So that's the first one. Here again you factor out b. b times the limit as h approaches 0 of g of x plus h minus g of x, everything over h. Now the question is, what is the limit in the first term and what is the limit in the second term? Look at our definition of limits. First principle. This is a times f prime of x. Remember how we defined f prime of x from the first principle? There is a limit as h approaches 0 of f of x plus h minus f of x over h. What about in the second term? That is the same as b times g prime of x. Again from the first principle. So we have shown that when you start with a times f of x, plus b times g of x, then your result should be equal to the constant a times f prime of x plus the constant b times g prime of x when you differentiate. I'm going to give you an example, e.g. examples. You can write find dy over dx given that in part A, y is equals to 4x cubed minus 2, let me say 2 times root x, then plus 7 over x minus 28. In part B, you're given that, let me look for a simpler one, where you have to use a linear combination. So let's say you're given that y is equals to 4 over root x plus, let's say minus, we cannot use a plus. Let's say it is minus 1 over x cubed. Then here you are adding 2 plus, let's say you have the cube root. This is cube root of x plus 17. Let's say plus 19. So we have those two. Let's work them out. Solution, let me choose another color. In part A, dy dx. But before I write dy dx, let me rewrite that function so that I can easily apply power rule of differentiation. So in part A, y can now be written as 4x cubed minus 2 root x is the same as x raised to 1 over 2. Then 7 over x is the same as, this is a plus, the same as 7 times x raised to negative 1. And then I can see minus 28. So with this one, it means that therefore, our dy over dx can be now written as, when you apply power rule, just differentiate the function. What is the derivative of x cubed? So here we'll have 4 times derivative of x cubed, which is 3x squared. Take note of that. Then minus 2. Again, differentiate x raised to 1 over 2. That will give us 1 over, remember we already differentiated it, 1 over 2 times x raised to negative 1 over 2. When you apply power rule, plus I can see the 7. Let us differentiate x raised to negative 1 using power rule again. That is negative 1 times x raised to negative 2. We are subtracting 1 from the power. Then minus, differentiate. Now, this is a constant term. Remember, we are talking of constant term, not constant times a function. It is a constant term, and so the derivative of that is 0. So when I simplify this one, I will now get 12 x squared You see these two and the other two will cancel. So it's like I have negative x raised to negative 1 over 2, which is the same as x raised to negative 1 over 2 is the same as 1 over x raised to 1 over 2, which is 1 over root x. So 1 over root x What about here? We'll talk of now 7 over x squared. Because when you take the negative power to the denominator, it becomes a positive power. So that's our derivative in part A. What about part B? How else can we write the given function? Y is equals to 4. You see, it is the same as 4 times x raised to negative 1 over 2. That's 4 over root x. Then minus x raised to negative 3. Plus, how do you write the cube root of x? Is the same as x raised to 1 over 3. That's the cube root. Then I can see there's a plus 19. So now when you differentiate this, we now talk of, this implies that, let me separate this because this is a new problem. So we partition that page into two. So that when I differentiate, we'll now be talking of dy over dx, dy over dx is equals to, apply power rule, it is 4 times differentiate x raised to negative 1 over 2. That will give us negative 1 over 2 times x raised to, now you subtract 1 from the power, so negative 1 over 2 minus 1 will become negative 3 over 2. Then minus, when you differentiate x raised to negative 3, that will give us negative 3 times x raised to negative 4. Then plus, bring down the power, that is 1 over 3 times x raised to, now what is 1 over 3 minus 1? That is negative 2 over 3. And 19 is a constant term that when you differentiate, you get 0. Remember here there was a bracket. There's a bracket here to enclose this. Very important. So that if I open the bracket, I'm going to get negative 2 x raised to negative 3 over 2. Then here we now have plus 3 times x raised to negative 4. Then here we have plus 1 over 3 times x raised to negative 2 over 3. And this you can also write another way, or just leave it as that one. Alternatively, you can write this as negative 2 divided by x raised to 3 over 2 plus 3 over x raised to 4 plus 1 over 3 x raised to negative 2 over 3. So that is our derivative. And you see how we have applied power rule. Power rule, you only apply them on the functions. Don't interfere with the scalars, the scalar multiples. But when you differentiate a constant term, take note, it is a constant term, not just a scalar multiple of a function. It is a constant term that when you differentiate, you're going to get a 0. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, to like, and to share this video. When we meet next time, we look at other techniques of differentiation, or the rules of differentiation. Yeah, remember, we still have some rules: the product rule, quotient rule, chain rule, etc. So we look at those ones when we meet next time. Bye bye.